Hello everyone. In this video, we will cover Chapter 13, Two Sample T-Tests for Comparing Two Means. We have already reviewed one sample t-test and the f-test. The methods for the two sample t-tests are generally the same as the one sample t-test. However, we will have the added question of, are these sample groups paired or unpaired, and do they have equal variances, where we will use the f-test. However, we will be doing most of the work for the two sample t-test in R. So let's get started. First, we have a slide of what's going on in this chapter. Two important notes for this semester. In this chapter, we are skipping the two sample z-test, which is found on the bottom of page 129 in your lab manual, and we are skipping the confidence interval for the difference between two population means, which is at the bottom of page 131. That is what we are skipping for lab. Lecture may be different. What is the purpose of a two sample t-test? Well, it's to test if sample means from different groups are different from each other, greater than or less than each other based on our interest in the experiment or research project. Some examples are a control group versus an experimental group, a treatment A versus treatment B, before and after exercise. And this test is done by testing a null hypothesis about the means of the two groups, just the same as a one sample t-test. There are three types of two sample t-tests. The first is called a student's t-test, and this is used for two sample groups with equal variances, otherwise called homoscedastic or homogeneous, that is measured by the f-test. The second type of test is called a Welch's t-test, and this is for groups with unequal variances. Finally, we have the paired t-test, and this is only used for observations that are made in pairs for each sample. And the paired t-test usually compares differences between the groups rather than the two groups directly. Here's a helpful decision flow chart for a two sample t-test. The first question we need to always ask with two sample groups is, are the data values paired in some way? If they are, we go directly to a paired t-test. If they're not, we're going to skip over the z-test part for lab, but of course, if you know the population variances, we're always using the z distribution. But for this lab class, we go to, are the population variances different? If they are different, we must use the heteroscedastic or Welch's t-test. If they are the same, we use the homoscedastic or student's t-test. The difference between independent and paired samples is somewhat confusing at times, but hopefully through this lecture and through the examples we do together, it will become more clear. Independent samples test two different test groups. The replicates in each group are assigned independently from each other and randomly. With independent samples, we must run the f-test to determine if we will be using a student's or Welch's t-test. In a paired t-test, the two groups are not independent from each other. Each replicate in the first group is related to a paired replicate in the second group. In paired t-tests, we do not run an f-test. A good example of this is before and after experiments. There is one person who is recorded on some measure before, and that same person is recorded after whatever treatment or experiment is done. The methods for the two sample t-test are very similar to a one sample t-test. I've highlighted the differences here. Otherwise, the methods are almost entirely the same. First, as always, we write out the hypotheses. The only difference here, now we're relating two sample groups. rather than a sample and a reference. We determine if this question is one-tailed or two-tailed, paired or unpaired. Step 2 is to choose the level of significance. Again, that is usually given, and it's usually 0.05. The third step, which is a new step for the two-sample test, is to choose the type of two-sample t-test. If it is paired, you move on. If it is unpaired or independent, you need to perform the F-test. The fourth step, which is slightly different than the one-sample test, is you must determine the degrees of freedom for the overall question, and we'll get into that in more detail in a few moments. The rest of the steps are the same as the one-sample t-test methods, determining the critical values, the calculated test statistic, comparing those values, finding the p-value, and making statistical and biological conclusions. Now we'll go into each of these steps in a little bit more detail where they differ from the one-sample t-test. First, writing out the hypotheses is slightly different because we are now comparing two groups instead of one group and a reference mean. Here I have a note regarding the subscripts, and I write that we should not write 1 or 2 for the subscript because that's not descriptive. It doesn't tell us anything about the problem. Instead, you should be using the actual descriptors from the problem in that subscript, and we'll see that in the example. In a two-tailed t-test, we don't care about the direction of the difference. We only ask if there is a difference. The null hypothesis is therefore that the mean of group 1 is equal to the mean of group 2, again, replacing group 1 and 2 with the descriptive words from that problem. The alternative is that the means of the groups do not equal each other. A one-tailed left two-sample t-test problem, the alternative hypothesis will be that the group 1 mean is less than the mean of group 2. The complementary null hypothesis is that the mean of that first group is greater than or equal to the mean of the second group. Again, reminder, the equal sign always goes in the null hypothesis. A one-tailed right problem, again, starting at the alternative, the mean of the first group greater than the mean of the second group. Null hypothesis is complementary, so the mean of group 1 is less than or equal to the mean of group 2. Step 2, find alpha. It's usually given. Step 3, choose the type of test and perform an F-test if necessary. If the replicates are paired, we must use the paired t-test and we completely skip the t-test. If they're not paired, we must compare the variances to determine if we will be using a Student's or Welch's t-test. This is a brief reminder on how to do the F-test. We have our null and alternative hypotheses, how to calculate F-calc, remembering to always put the larger variance in the numerator and the smaller variance in the denominator, calculating F-crit and the p-value from there. If you accept the null hypothesis of the F-test, which is that the variances of the two groups are equal, this means we use a Student's t-test. The Student's t-test is slightly more powerful than the Welch's t-test. If, however, we reject the null hypothesis of the F-test, this means that the variances are not equal, and this would cause us to use a Welch's t-test. The fourth step, which is slightly different for two-sample tests than one-sample tests, is we will determine the degrees of freedom for the question. This is different for each type of two-sample t-test, and we'll discuss those in a moment, but that also comes with a caveat, which I will discuss then. Step 5 is determining the critical values. This is done in the same way as for the one-sample t-test using the t.inv or t.inv2t functions in Excel, or using the t-value table in your book. Step 6 is to calculate the test statistic. This is also different for each two-sample t-test. But step 7 is familiar. We compare the t-critical and t-calculated values using our regions of rejection on a distribution that we've drawn. Step 8 is to determine the p-value. We can use the way we've used before, which is t.dist or t.dist.2t or .rt. You can also use another function in Excel called t-test, using the first set of values, the second set of values, and then entering arguments about what type of tailed test this is and what type of test for paired students or Welch's. This is reviewed in your lab manual, and I will not review it in the Excel sheet at this time. Steps 9 and 10 are also familiar, drawing our statistical and biological conclusions from the data. These next slides have a lot of complex equations on them. I'm not going to go into them in much detail because we don't need to use them in lab. They are here for your reference for lecture problems where you may need to calculate some of these variables by hand. Really, the takeaway from this for lab is the calculations for t-calc and variance are different for each type of t-test. Here we have demonstrated a student's t-test. The student's t-test uses a pooled variance formula. This is because every value of the variance is assumed to estimate the population variance, or sigma squared. So, in theory, we should be able to get a better estimate of sigma squared by pooling the sample variances with that formula seen on the previous slide. However, if the variances are not equal, we cannot pool them, and that would lead us to a Welch's t-test, which has a slightly different formula for t-calc and a very different formula for the degrees of freedom. Again, you do not need to worry about this formula for lab. We'll next discuss the paired t-test. The purpose of these is slightly different, and it's to compare the differences between means of two groups of paired observations. In theory and in practice, a paired t-test is really just a one-sample t-test that compares the differences of the data sets to a hypothesized mean of 0. What this means is the paired t-test is a more powerful t-test than the independent t-test, but we can only do it if the data are already paired for samples or individuals. The hypotheses for a paired t-test are slightly different because we are comparing differences instead of groups. Here, the null hypothesis is the mean difference, with a capital D for difference, is equal to 0. The alternative is that that difference is not equal to 0. There is a way to do this in Excel as well, but we will mostly be focusing on doing this in R. Finally, the paired t-test, t-calc, and degrees of freedom also come with different formulas than those we've seen before, but we will not be using these because we can do these problems in R. The last slide I'm showing here is the practice problems you can use to study for the t-test chapter. We will go through worked examples 1 and 2 during this video. There are also several practice problems in the lab manual you can do to practice two-sample t-tests. Those are listed here. The problems are worded somewhat differently, and what I would like you guys to do is to just do two-sample t-tests following the methods that we'll see in the worked examples. So let's get started with the worked examples. First, I'll open up page 133 in the lab manual to see worked example 1. In this problem, the researchers have collected the body weights of a bird called cactus wrens and are interested in if there's differences among these three groups of males, females, and juvenile cactus wrens. This problem tells us to compare the weights of the males to the weights of the juveniles, ignoring the females, and testing these hypotheses. The null being the mean weight of the males is less than or equal to the mean weight of the juveniles, and the alternative that the mean weight of the males is greater than the mean weight of the juveniles. This will be a one-tailed right t-test. Let's open up this data in Excel, and here I have open the Chapter 13 Excel template. And what you'll notice is this template looks very long and very complicated if you go through the different tabs. However, we're not going to do this in Excel. We are only going to use Excel to get the data and start kind of thinking about the type of problem we want to do. In this problem, we have the weight of the male, female, and juvenile birds, and we'll start by describing what type of test we want to do, and with our hypotheses, move into R and start testing this data. This will be a two-sample t-test. I'm going to type that in down here in this t-test description table. We'll be comparing the males and the juveniles according to the instructions of the problem. Since the hypotheses were already given to us, we know that this is a one-tailed right t-test. By type of t-test, I mean, is this a student, Welch's, or paired? The first question we ask is, are these data paired? The answer is no. These are different birds. They don't have relation between male and juvenile. For example, this data for this bird does not pair with the data from this bird, or this bird, or this bird. So this is an unpaired test. What that means, if we follow our flow chart, is we need to do an F-test to check the variances and determine what type of problem we will do. Before we do that, let's go ahead and add our null hypotheses. If the hypotheses were not given and we were starting with the information that we wanted to do a one-tailed right t-test, we would start with our alternative hypotheses and say that the mean for the males, and I'll put that in parentheses, is greater than the mean of the juveniles. And I'll expand this column just a bit so we can see that. Then we write the complementary null hypothesis. The mean of the males is less than or equal to the mean of the juveniles. The text I'm writing here in parentheses would be the subscript for these mu values. In this problem, we'll use an alpha of 0.05. The F-test can be performed here as we did in the previous lecture video, but we're going to go ahead and do that in R. So first we need to load the data into R. I'm going to copy all of the body weights for these birds and make a new document, paste them in. It's already in column format, so this is ready to be saved. I'm going to save this to my desktop, and this data I'm going to just call Chapter 13, and I will save it as a CSV. Remembering to only choose the normal CSV option. We'll say yes, it's okay that it's in CSV format. And let's open up RStudio. If it looks like this, we need to open a new script. And even if you already have a script up, you need to open up a new script to start working on this anyway, so we can save the analysis for this chapter. Remember that R doesn't know where our data is, so we need to set the working directory, choosing the directory where we stored our CSV file. I saved mine on my desktop, so I will open the desktop folder, and we see it print out set working directory to the desktop. Now that I'm in the right folder, I can load in the data. This data I will just call Chapter 13, because in a few moments we will add more data to it. We're going to assign it using the arrow symbol and use read.csv to read in the data. Remember to use quotations around the name of the file. I called mine chapter13.csv, and I used the tab button to fill out the remainder of that name. Finish the quotation. We need to tell R that this data has a header or a column name, so we'll say header equals true. Running this line using Control-Enter on your keyboard or clicking Run here. The Chapter 13 variable has now been assigned the data from this file. As always, we want to look at the first 6 lines of data using the head command. So I will use head Chapter 13, and there we see printed the males, females, and juvenile data. Let's review what type of test we want to do. What type of test will we do? First of all, is this a 1 sample or 2 sample t-test? This is a 2 sample t-test because we will be using the male and the juvenile data. Because it's 2 sample, our next question, is it paired or unpaired? This is unpaired data because, again, the single bird from the male data has nothing to do with a single bird from the juvenile data. Because this is unpaired, we next must ask, is this an equal variance problem or unequal variance? And how do we know that? We have to check using the f-test. From the previous video, we used the var.test function to compare variances between 2 sets of data. We will use the data from Chapter 13, column males. Again, I use tab to fill that out. And Chapter 13, using the column juveniles, using tab to fill that out. I'm going to run this line. Let's take a look down here at the results, and we see the data we used, males and juveniles, the F value, degrees of freedom, and here is what we're looking for, the p-value. Since the p-value of 0.47 is greater than 0.05, we accept the null hypothesis of the f-test. So since p is greater than alpha, we accept the null hypothesis of the f-test, meaning we use the students or equal variance t-test. If the variances were not equal, we would reject the null and use the Welch's t-test. Continuing with this problem, we next asked, is this one-tailed or two-tailed? And as we discussed on the Excel sheet, this is a one-tailed to the right t-test. Now we have everything we need to run a 2-sample, unpaired, one-tailed right, equal variance or students t-test. I wrote this line out because it's important to describe the type of test you will be doing before you actually run it, because this determines the arguments you will use in the function. Let's go ahead and do this. We'll use the same t.test function that we've been using. We'll call from Chapter 13 data the males, and the second input, now this is different from the 1 sample t-test, In the one sample t-test, we used mu equals and entered the reference mean. For the two sample t-test, we will now just enter our second set of data. In this case, it's the juveniles data. Since this is a one-tailed hypothesis, we need to use the alternative argument and set it to greater for a right-tailed test. The last thing we need to do with this function is set the variances to equal. We need to tell R that we want it to run a student's t-test. To do this, we will use the argument var.equal. Press tab to select that. And this is a true or false. In this case, we know the variances are equal, so we set var.equal to true. Running this test only takes a moment, and even though we spent some time figuring out what type of test to do and typing in the function in R, this would have taken up to 20 minutes in Excel. So I strongly recommend using R for a two-sample t-test. I will post a filled Excel sheet if you would like to see how it's done in Excel. You may also use the data analysis tool pack in Excel, but I will not be going over that in this video because it is in the lab manual and you can learn it from there. Let's take a look at the results that we produced using this t-test function. This ran a two-sample t-test using the data from Chapter 13 males and Chapter 13 juveniles. That's what we wanted to compare. We have our t calculated value here, 2.5458. This is the pooled degrees of freedom, and our p-value of 0.007803. We have a 95% confidence interval here, but it doesn't really mean anything for a two-sample t-test, so we're not going to look at that any further. It does also give us the mean values of our two groups. However, what we want to focus on is just this first line, the t-calc value, the degrees of freedom, and the p-value. Let's look at the t-value first. Just as with a one-sample t-test, we can also compare the t-calc value to the t-crit value. Let's go into Excel to calculate our t-critical values. I'm just going to put that over here. In fact, I will write out the answers we have so far. So our t-calc value was I'm sorry. I'm writing this in the wrong table. Just for clarity, I'm just going to move it down here. Our t-calc value that we got from R was 2.546 or 5458. Our t-crit value we'll find using the t.inv function. This is a right-tailed test, so we need to use equals negative t.inv. Our probability was 0.05, and from R, we know our degrees of freedom for the overall problem was 34. This gives us a t-crit value of 1.691. T-calc is greater than or more extreme than t-crit, meaning we would reject the null hypothesis. Let's see if that matches our results from R. Here, the p-value, 0.0078, is less than our alpha of 0.05. This also indicates that we should reject the null hypothesis. Our t-value and p-value conclusions match, so we're good to go. Let's go ahead and write this down. Since p is less than 0.05 and t-calc is greater than t-crit, we reject the null hypothesis. this is our statistical conclusion. Now our biological conclusion, let's take a look at our null hypothesis again. We are rejecting the null hypothesis that the mean weight of the males is less than or equal to the mean weight of the juveniles. We are accepting that the mean weight of the males is greater than the mean weight of the juveniles. Let's go ahead and write that in R. There's space here in Excel as well, but I'll just keep it in R for now. The mean weight of the male birds is significantly greater than, this is the alternative hypothesis, significantly greater than that of the juvenile birds. That concludes how to do a equal variance two sample t-test in R. If the variances are not equal, all you need to change in this line is var.equal and set it to false. I'm going to run this line and you'll see now this changed to a Welch's two sample t-test. So our first output just said two sample, that was a student's t-test. This one where we set var.equal to false ran a Welch's unequal variance t-test. On the Excel template and in your lab manual, this problem is done using both a student's and Welch's t-test. However, I am not going to go through those here because we can do them in R much faster and easier. The next problem we will look at is worked example 2. Let's go ahead and look at this in the lab manual on page 136. And let's go ahead and read this problem. So the following data are cholesterol levels from 10 adult males selected from a larger study. This experiment was set up using a paired design because the researchers suspected that there would be variability in overall cholesterol levels among different adult males. Each subject was randomly assigned one of two types of meat to begin with, and each individual ate beef or pork as their primary meat source for 20 weeks, had their cholesterol measured, and then switched to the other meat for 20 more weeks. The individuals are the replicates, but there's two measurements from each individual. And this is the key to identifying a paired t-test. If you have individual replicates with two measurements from each individual, that is a very good clue that we will be using a paired test. Let's scroll down to the data and only looking here at the subject, beef and pork, these are the cholesterol levels of these individual men on their diets of beef or pork. This table is used in Excel to do this problem, and the paired t-test is slightly easier to do in Excel, but again, we have R, so we're going to use this in R. Starting in Excel, though, to look at the data, let's talk about what kind of problem we're going to do. As we mentioned, this will be a paired t-test. This is a two sample t-test, and I didn't leave great space for this, but I'm going to go ahead and type that in here. Two sample t-test, it is paired. And in this question, the researchers are only interested in if there is a difference between the cholesterol levels. That would indicate that this is a two-tailed test. Next, we will look at our alternative and null hypotheses for this test. And I have two spaces here because there are two ways to write this. The first way to write this is what is listed in the lab manual and in the PowerPoint slides, which is that the mean difference is equal to 0. However, that's a little bit hard to conceptualize. So another way to write this is that the mean cholesterol for the beef diet is equal to the mean cholesterol of the pork diet. And this makes sense because if we subtract mean pork from each side, we have U difference equals 0. Both of these answers are correct for the hypotheses of a paired t-test. Then the alternative, we can have the mean difference does not equal 0, or also correct, the mean cholesterol of beef, here we go, does not equal the mean cholesterol levels. Oh, it didn't do it. Let's try that again. Insert, there we go. Equal the mean of pork. Great. I left space here for those of you who would like to do this in Excel, but we're going to go straight into R. And the way we're going to do this is copying the data onto the same CSV sheet we already used. So we'll take the cholesterol levels for the beef diet and the pork diet, copy that, opening up my Chapter 13 CSV file, pasting it at the top. Remember, we have to save this file again, telling our computers that the file has been updated. Yes, we want the CSV format. When we go into R, we need to reload the data because we have updated and R doesn't know that yet. If we run line 1 to read the data in again, and line 2 to see the data, we see how it's changed to have both the females, males, and juveniles data from the birds question, and it also now has the beef and pork data from worked example 2 that we just added. Coming down here to the bottom of the script, I'm going to enter down a couple of lines to space these problems out. And we are going to run a paired two-sample, two-tailed t-test. Remember, for paired or unpaired, the paired test, we do not need to run a pre-test f-test. To run a paired test in R, we will use t.test. Our data is coming from the Chapter 13 variable, and we are using the column beef, comparing that to Chapter 13 column called pork, and we will use the argument paired equals true. This tells R to run a paired t-test rather than an unpaired t-test like we did for the first worked example. Let's run this line. And looking at the output, we've run a paired t-test on the data, Chapter 13 beef and Chapter 13 pork. Here we have our t-calc value. And again, we would find our t-crit value in Excel. The degrees of freedom, it is slightly different for paired. Here it is 9, and our p-value of 0.001108. Let's go ahead and type some of this into our Excel sheet. I'm going to start here, but you can put this anywhere on this sheet. And first we have our t-calc value that was given to us in R. It was 4.708. We also have our degrees of freedom from R. It was 9. Let's find our t-crit value. And for this one, this is a two-tailed, so we can use t.inv.2t using our alpha of 0.05 and our degrees of freedom of 9 to get 2.62 and a lot of numbers after that. Remember, we can shorten this by, on the Home tab, clicking on one of these buttons here. This is to increase the number of decimal spots, and this is to decrease. So we'll make that a little bit shorter so it's not so long. And for a two-tailed t-test, we need two t-critical values. The second one is just the negative of the first one. So we have negative and positive 2.262. Our t-calc value is more extreme than either of the t-crit values. This tells us to reject the null hypothesis. Let's take a look at our p-value. The p-value is 0.001, which is less than our alpha of 0.05, which also indicates that we need to reject the null hypothesis. So again, our t and p-value conclusions are the same. Let's go ahead and type in our statistical conclusion. Since p is less than 0.05 and t-calc is greater than t-crit, we reject the null hypothesis. For our biological conclusion, let's take a look at our hypotheses again. Our null hypothesis was that there was no difference between these two diets, or that the mean cholesterol level for beef was the same as for pork, and we are rejecting this null hypothesis. So we use our alternative hypothesis as our conclusion. Let's type that into R, and we can say there is a significant difference in cholesterol levels in men eating beef diets versus pork diets. Your lab manual solutions goes into a little bit more details, talking about which one is greater, and that's fine if you want to go into that detail, but this level of conclusion is sufficient for the lab portion of this class. The last thing we'll do is save this file. File, save. I'm going to continue saving on my desktop, and this one I'll call Chapter 13 Analysis. There are several more problems in your lab manual that I highly encourage you to do. Those are listed on the PowerPoint slide here. And again, the wording of the question tells you to do some different things. All you need to do for practice for the lab portion of this class is a two-sample t-test using the data in these problems. With that said, this concludes the video on the two-sample t-test.